Game theory is the study of mathematical models of conflict and cooperation between intelligent rational decision-makers. Game theory is mainly used in economics, political science, and psychology, as well as logic, computer science, biology and poker. Originally, it addressed zero-sum games, in which one person's gains result in losses for the other participants. Today, game theory applies to a wide range of behavioral relations, and is now an umbrella term for the science of logical decision-making in humans, animals, and computers. Modern game theory began with the idea regarding the existence of mixed strategy equilibria in two-person zero-sum games and its proof by John von Neumann. Von Neumann's original proof used Brouwer fixed-point theorem on continuous mappings into compact convex sets, which became a standard method in game theory and mathematical economics. His paper was followed by the 1944 book Theory of Games and Economic Behavior, co-written with Oscar Morgenstern, which considered cooperative games of several players. The second edition of this book provided an axiomatic theory of expected utility, which allowed mathematical statisticians and economists to treat decision-making under uncertainty. This theory was developed extensively in the 1950s by many scholars. Game theory was later explicitly applied to biology in the 1970s, although similar developments go back at least as far as the 1930s. Game theory has been widely recognized as an important tool in many fields, with the Nobel Memorial Prize in Economic Sciences going to game theorist John T. Roll in 2014. 11 game theorists have now won the Economics Nobel Prize. John Maynard Smith was awarded the Crawford Prize for his application of game theory to biology. Representation of games. The games studied in game theory are well-defined mathematical objects. To be fully defined, a game must specify the following elements: the players of the game, the information and actions available to each player at each decision point, and the payoffs for each outcome. A game theorist typically uses these elements, along with a solution concept of their choosing, to deduce a set of equilibrium strategies for each player such that, when these strategies are employed, no player can profit by unilaterally deviating from their strategy. These equilibrium strategies determine an equilibrium to the game, a stable state in which either one outcome occurs or a set of outcomes occur with known probability. Most cooperative games are presented in the characteristic function form, while the extensive and the normal forms are used to define non-cooperative games. Extensive form. The extensive form can be used to formalize games with a time sequencing of moves. Games here are played on trees. Here each vertex represents a pointer choice for a player. The player is specified by a number listed by the vertex. The lines out of the vertex represent a possible action for that player. The payoffs are specified at the bottom of the tree. The extensive form can be viewed as a multiplayer generalization of a decision tree. The game pictured consists of two players. The way this particular game is structured, player 1 moves first by choosing either F or U. Next in the sequence, player 2, who has now seen player 1's move, chooses to play either A or R. Once player 2 has made his/her choice, the game is considered finished and each player gets their respective payoff. Suppose that player 1 chooses U and then player 2 chooses A. Player 1 then gets a payoff of 8, and player 2 gets a payoff of 2. The extensive form can also capture simultaneous move games and games with imperfect information. To represent it, either a dotted line connects different vertices to represent them as being part of the same information set, or a closed line is drawn around them. Normal form. The normal game is usually represented by a matrix which shows the players' strategies and payoffs. More generally, it can be represented by any function that associates a payoff for each player with every possible combination of actions. In the accompanying example there are two players, one chooses the row and the other chooses the column. Each player has two strategies, which are specified by the number of rows and the number of columns. The payoffs are provided in the interior. The first number is the payoff received by the row player. The second is the payoff for the column player. Suppose that player 1 plays up and that player 2 plays left. Then player 1 gets a payoff of 4, and player 2 gets 3. When a game is presented in normal form, it is presumed that each player acts simultaneously or, at least, without knowing the actions of the other. If players have some information about the choices of other players, the game is usually presented in extensive form. Every extensive form game has an equivalent normal form game. However, the transformation to normal form may result in an exponential blow-up in the size of the representation, making it computationally impractical. Characteristic function form in games that possess removable utility, separate rewards are not given. Rather, the characteristic function decides the payoff of each unity. The idea is that the unity that is empty, so to speak, does not receive a reward at all. The origin of this form is to be found in John von Neumann and Oscar Morgenstern's book. When looking at these instances, they guess that when a union appears, it works against the fraction as if two individuals were playing a normal game. The balanced payoff of C is a basic function. Although there are differing examples that help determine coalitional amounts from normal games, not all appear that in the function form can be derived from such. Formally, a characteristic function is seen as where n represents the group of people and is a normal utility. Such characteristic functions have expanded to describe games where there is no removable utility.